In this video, we're going to get a little abstract to introduce representations and segue into a topic which is going to lead us to the most useful properties of symmetry and group theory for molecules. So let's look at the D2H point group here. This has 8 symmetry elements. We have E, C2, C2 prime, C2 double prime, sigma H, sigma V prime, and I. So we have, let me go ahead and just put in the I there as well. Make sure that's at the center. Okay, so each of these, if we imagine some vector u is defined by its components in the x, y, and z direction on the coordinate system that I've drawn here. Okay, so each of these elements has an associated operator, which is going to have some defined effect on this vector if we act on it with that given operation. So for example, if we start with the identity element, or the identity operator, E acting on ux equals ux, it leaves it unchanged. E acting on uy equals uy, it leaves it unchanged. E acting on uz equals uz. Okay, so that all seems simple enough. The identity element just leaves things unchanged. So another way we could write this is to turn this into a matrix operating on this vector. So for example, if we have the vector ux, uy, uz, this is equal to the identity element, the identity operator leaves that unchanged. So what would be the matrix operator which would leave this unchanged? It would be the following matrix. It would just be a 3x3 identity matrix. Okay, so that all seems simple enough for now. So we can represent the identity operator as this particular 3x3 matrix in terms of its effect acting on a vector in this 3D coordinate space. Okay, so this matrix here is said to be one representation of E. So I could say, you know, this particular matrix is a representation of E in the D2H point group. Okay, so that seems straightforward and simple enough. So what about other operators that we've got going on here? So for example, if I take C2, C2 is a rotation around the z-axis in the xy plane. So if I take C2 acting on ux, that's going to give me minus ux. It's going to rotate me around 180 degrees. So whatever direction I was pointing in the x direction, I'm the reverse of it now. C2 acting on uy is going to be the reverse of that. It rotates around 180 degrees. Now whatever direction I was pointing in y, I'm pointing in the opposite direction. And if I act C2 on uz, well, the z component is unchanged by the rotation around the z-axis. So that z component is unchanged. So if I do this same type of matrix algebra here, what I can determine is that the C2 operator, my representation of it, would be -1, -1, 1 along the diagonal and zeros on the off diagonal. So that would be the representation of the C2 axis, or the C2 rotation operation. If I do it for C2 prime, C2 prime is a rotation around y, you can convince yourself that I'm going to have this representation. It's going to be the same thing. X and z are now flipped and y stays the same. And you might guess that for C2 double prime, that operator, which is a rotation around x, leaves x unchanged, and we go -1 for y and z. So this is our 3x3 matrix representation of C2 double prime in the D2H point group. Okay, and all of the operators we can form a representation for like this. Sigma h. Sigma h is going to leave, it's a reflection through z, through the xy plane of z. It's going to leave x and y untouched, and it's going to be the opposite of z. So that's going to be 1, 1, minus 1. Sigma v is the same thing, but sigma v is a reflection through the xz plane, so it's going to invert y. And now the pattern, you might guess, that's sigma v prime. It's going to be the same thing, but we flip x, keep y and z the same. Okay, so I have all of those, and the last one I'm going to write is the representation of I. I is inversion through the center. It's going to flip the x, y, and z coordinates to the opposite of themselves, still not having any off-diagonal contribution. So I is minus 1, minus 1, minus 1. Okay, so you notice that for all 8 of these operators, I now have a representation of them in this D2H point group that is a 3 by 3 matrix. So this is a 3 by 3, or a 3-dimensional representation of these operators in this specific point group. So as we're going to see in future videos, this is one possible representation of these operators in this specific point group. But there are many different ways we can represent operators, and there's one particular set for every point group, which are the simplest possible representations you can have. Those representations are going to be called irreducible representations, and they're going to be very important for helping us determine what properties of molecules are predetermined just by their symmetry before we know anything else about the molecule.